All right, well, today, obviously I'm not there. This lecture will just go for about a half hour. We'll see how it goes. I'm back to teaching in my basement, which is like bringing back some PTSD. Anyway, please make sure you pay attention. I'll post this as well on Canvas if you need it. So let's just go ahead and pick up where we were. The plan today is to wrap up everything and then maybe getting to the naming and formula writing. If you need the substitute deposit at any time, just raise your hand and let them know. So the first thing we're going to talk about is mass spectroscopy. And this is on the AP test. It's just usually 1 or 2 multiple choice questions, and we'll review it right before the test, but it's kind of nice to get an idea. So mass spectroscopy is how we figure out the abundance of isotopes in different atoms. So you can read a little bit there, but they take this sample, they turn it into a vapor, they charge it, and then shoot it around these corners. And then just in this image, as you can see, as they go around the corner, my slate is dead. We'll see if it charges. They deflect at different angles based on their charge to mass ratio. And based on the angle that they bend, we can then see that there's more than one type of ion. So they have ZR, zirconium here. And they found that there was 1, 2, 3, 4, 5 different paths that the particles separated into for zirconium. That would mean there are 5 isotopes. The one that has the highest relative abundance, we would not necessarily call that the isotope. That would be the one we would list on the periodic table. But when we found its mass, that average mass, we would take 90 and multiply it by like 52%, 91 by like 10 or whatever, and we would do that same math we did yesterday. We multiply the fraction by the mass of the isotope, and we go from there. All right. Where'd my pause button go? Okay, sorry about that. My boss just called. Mrs. Kent, or texted. All right, so back here. So on the AP test, you'll get a question, and you'll have a graph that looks something like this. And it would, on the left, it has the relative number of atoms. So that's like our percentage of the 2 isotopes, and then the mass ratio. And we don't have to worry about exactly what that means. We would just have to say, all right, if this was a test question, we would say that copper with the mass of 63 is the non-isotope because it's the one in greatest abundance, and copper with 65 is the isotope because it's less abundant. Then once again, we could do the math. We could take our 0.69, oh, this is supposed to be a marker. I'm writing with my finger, times the 63, and then we'd take our 0.31 and multiply that by 65, and we could do that math to find the average atomic mass of the isotopes. That's a skill you need to be able to do, and you should be able to do it from a graph with data like this. Okay, another example, and I can have the substitute posit would be these 3 questions. So go ahead and pause it and see if you can answer these questions. Okay, so probably need to give you a little more information before I did that, and the answers were right here. Let's just talk through them, and hopefully they kind of make sense. So the answer to number 1 is D. The reason why it is D is in isotopes, we change the neutrons, but we do not change the protons. So anything that would say something about the protons changing would definitely be different. Okay, number 2, it's a little bit tricky, but not too bad. The identity of compound Y is, it's one of these four. So you would need to look over at the periodic table, and if you look at all of these, no peak is really too high or too low. So the 99 is the highest, but if we want to be able to answer this, we kind of have to know the average mass, and we're between 92 and 100, and I would say we're probably around in the middle. So we would look at the periodic table and we try and find a mass that's around 95 or 96. Americium and einsteinium are way heavier. Zirconium is just underneath, if I remember right, and molybdenum is right there in that range. It's at 94, 95, 96, if I remember correctly. So once again, you look, and you don't have to do the exact math, because usually the ranges of the questions will eliminate the ones that are way off. Then just do your best estimate of what that mass number would be, and then you'll find your answer. Number 3, which peak comes from an atom with the greatest number of neutrons? Okay, so that's the one that's the heaviest, and so that would be letter D. Okay, hopefully those make sense. We will review these again before the actual AP test, but they're typically not the hardest questions, and they're usually just in the multiple choice. All right, chemical formulas. Now we're starting to get into stuff we'll use quite a bit. They symbolize, well, this is the learning objective, so we'll just go past that. So first we have what we call the molecular formula. And that's a representation of a molecule or compound which consists of the following: the chemical symbols to indicate the types of atoms, and a subscript. So like H2O would be a molecular formula. The subscripts tell you how many of each atom there are. All right, subscripts are only used when more than one atom of a given type is present. So carbon monoxide is CO. We don't put C1O1. We only use it if there's more than one. A structural formula shows the same information as molecular formula, but also shows how the atoms are connected. So an example of that is acetic acid is HC2H3O2. All right, you will often see it also as HCO. What is it? I think then H again, and what am I missing? And there's like 3 H's or something. And this is wrong. I can't remember exactly what it is. But this shows you kind of how they're connected. That's the structural, and that's less common. This shows you the actual ratio, and that's the molecular formula. So that was not a very good representation. I should have looked at that before I tried to get it from memory. Okay, sometimes we'll use this one most. This shows you kind of the spatial arrangement in a two-dimensional thing. This shows you the three-dimensional, and this is called the space-filled model that shows you the actual space the molecules are taking up. But we really, really need this. And then this. We never use these too much. I don't know. We use this a little, but never part D. Okay. You need to absolutely know and memorize. Oh, that's the worst rectangle ever. You need to know the diatomic molecules. H, N, O, F, C, L, B, R, and I. All of them, when they are alone, come with their best friend. So they are two atoms or diatomic molecules. Now, most elements consist of just a discrete individual atoms. So if we were writing sodium, we would just put Na. But if we're writing chlorine, we put Cl2. Chlorine is so reactive that when it's absolutely alone, it finds another chlorine and they hang out. So please, please memorize this. There's a statement, it's more like college worthy, but it says, have no fear of ice cold beer. Now, hopefully you guys aren't drinking beer, but whatever. That's the saying that they'll teach you in college. Have no fear of ice cold beer, and those are your elements that are diatomic. You're welcome to adjust that. Let me pause for a second. Okay, never mind. I don't need to. Okay, next. Sulfur is an odd one, and it's diatomic, but it's octatomic. It's safer when it's in these rings, but you don't need to really worry about that. Okay, an empirical formula indicates the simplest whole number ratio of the number of atoms in a compound. A molecular formula indicates the actual number of atoms of each element in a compound. And so they have these just written here. Benzene, its molecular formula is C6H6, but its empirical is just the ratio of C's to H's, so it's just C and H. And then acetic acid, it's C2H4O2, and then empirical formula CH2O. This is a little wrong. The molecular formula is never, that's the structural, it's HC2H3O2. So maybe in the book we're using, they write it that way, but usually it's this way 100% of the time. All right, then it just talks about titanium dioxide as an example. That's in your sunscreen, and this guy's hairy legs. And you're welcome to read that in the book. Then vinegar, and then isomers we don't deal with in AP, but an isomer is where it has the same formula, but the structures are different, and that's your plastics. Many plastics are just isomers of each other. Okay, so there's just two, acetic acid and then methyl formate, same stuff, just arranged in a different way. And you'll learn this in college if you take organic, but none of it is in AP. Okay, I'm going to go over the periodic table super fast. Dmitry Mendeleev and Lothar Meyer, they are credited with arranging the periodic table in a way that makes sense. All right, they took things that had similar properties and they put them into vertical columns. Okay, and the ones that were heavier went lower. That was what they did. So both of them published tables with the elements arranged according to increasing atomic mass. Mendeleev used his table to predict the existence of elements that would have properties similar to aluminum and silicon, but was not yet there. Once they discovered gallium, it fit exactly where Mendeleev thought, and that kind of sealed the deal that the periodic table was a good way to organize it that made sense and was justifiable through science. Okay, this is the first one, and you can look at that in your notes on the app or as you read. It's a little bit crazy to look through, but it does make sense, and it's the same basic structure we have today. All right. By the 20th century, it became apparent that we were dealing with protons, or atomic numbers, not just atomic masses. And that was a big change, but it still was supported by the data. Then, periodic law, that's why we call it the periodic table. It says the properties of the elements are periodic functions of their atomic numbers. So that's a nerdy way of saying the properties repeat themselves in these vertical columns. All right. The modern periodic table arranges the elements in an increasing order of their atomic numbers and groups atoms with similar properties in same vertical columns. Okay, and we will learn a lot, but make sure you're aware that the metals are here. Then the nonmetals are here. And then in the middle, we call these metalloids. The metalloids just kind of reside right there. Pretty hard to circle with my finger, but you can look that up in your text on your app and you can see a better detail of that. But make sure you know where metals, nonmetals, and metalloids are on the periodic table. Metals are shiny, malleable, good conductors of heat, electricity. Malleable means that they bend instead of they break. So if I hit a metal with a hammer, it will dent. It usually will not shatter. Non-metals, they are brittle. All right, they'll shatter if you hit it with a hammer. They appear dull. They are not good conductors of heat or electricity. And metalloids kind of live in between, so they do both moderately well, but they have some properties of metals and some properties of non-metals. Okay, and I'm going to skip through here, that part. These are the ones that you need to know their names of and their location. Alkali metals, alkaline earth, halogens, and noble gases. We don't need to know the pycnogens or the chalcogens, their names, but we don't need to know them. But we definitely need to know that family 1 and 2 are alkali metals, except hydrogen. Excuse me. Alkaline earth metals, that's group 2. That's where your alkaline batteries come from. Then your halogens, that's group 17. That's like your halogen light is made with chlorine. It's a halogen. And your noble gases are on the far right. They're the ones that don't react. So make sure you know those 4 names and the families that they live in. All right, let me pause it for a second. If you need to write those down, go ahead and have the substitute stop. All right, so this just shows their location. All right, got my slate going now. It shows their location, so alkali metals, alkaline earth, transition metals. Make sure you're aware of where those are, just dead in the center. These are fine to know, but you don't have to know them, but we absolutely need to know them. So these 4, and then definitely the transition metals, which I forgot to mention before. So if you would, take a second, and we can just draw this out. Draw in your notes a rough periodic table. Oh my goodness. My slate's a little crooked, I guess. So families 1 and 2, oh my. We need to know the names of those. So alkali and alkaline earth. We need to know this area. And it really is like this area here. Those are the transition metals. And then we need to know family 8 are the noble gases. Why is this so messed up? And then family 7. Oh my gosh. And those are the halogens. I hope you're enjoying this as much as I am. And then add to this that these are your metals. Okay, and that was supposed to be written sideways. This little staircase, these are your metalloids. This is terrible. And these are your non-metals. So if you need to pause it, go ahead and do that. All right, then 2.6 molecular and ionic compounds. So we'll jump into that. In ordinary chemical reactions, the nucleus of each atom and thus the identity remains unchanged. So when we say ordinary chemical, we mean not nuclear reaction. So in our class, in a reaction, the identity of the element remains unchanged. Electrons participate in chemical reactions by being lost or gained. The gain or loss of electrons results in the formation of ions. So like sodium is in family 1, it wants to lose its lone electron. So it will become an ion of +1 by losing 1 electron. Now it can't lose it just to nowhere, so someone had to take it. So something like chlorine, oh come on, there we go. It had 7 valence electrons, and we'll learn about these drawings later, so you don't have to know them exactly. It wants 8, so chlorine will take it. It becomes a -1. Then I have a cation here. I have my anion here, and they will form a bond when they do that because the plus and the negative attract each other. When 2 ions stick together because of their attraction, we call it an ionic bond. So an ionic bond is a bond between 2 ions. Okay. And this is just going to say pretty much the exact same thing. My sodium nucleus, I have 11 electrons, but it wants to lose 1. It only wants 10. It wants to become noble. It wants to become like neon. Neon is element number 10, it has 10 electrons. And if sodium can lose an electron and become Na+, it becomes similar to neon. Chemically, it becomes the same, but physically, it doesn't change into neon. It just behaves chemically like neon. And that would be this ion here. The Na+ ion is now non-reactive. It's stable. The sodium lost the electron it didn't want, so it became a positive cation. Okay. Now, I think I talked about this yesterday, but it says the periodic table can serve as a guide for predicting the ionic charge of main group elements. Many main group metals lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. All right? So main group, by the way, means non-transition metals. So it's everything but the transition metals. So we said this yesterday. So group 1, it loses 1 electron and forms a positive 1 cation. Now, +1 or 1+, they're slightly different in what they mean, but they don't really matter. I always write +1. Some books put 1+. And they represent pretty much the same thing. Group 2 always loses 2 to make a +2. Then nonmetals, it's the same, but the reverse. They gain instead of lose. They gain enough electrons to give them the same number of electrons as an atom of the next noble gas. So 17, or what I call group 7, they gain 1 to become like group 18 or 8, the noble gases. Oxygen, their family, they gain 2 to become a -2, and nitrogen, that family, they gain 3 to become a -3. So when we're using just these basic main group metals and nonmetals, it's pretty easy to predict their ionic charge. All right, this is in the text. It just says the same basic idea, so I'm going to skip through that. All right, so as we move from far left to far right, positive charges of cations are equal to the group number. Moving from far right to far left, negative charges of anions are equal to the number of groups moved left from the noble gases. So if I draw, once again, I hit the eraser. I don't really know what's going on here. Okay, so this is a little bit better. So it's just saying as I go that way, I become positive equal to the number of families I went over. Now remember, we're skipping these. But then it's saying if I'm going this way, I become negative based on the number of times I moved away from here. Okay. This method is less reliable for transition metals in here, so that's why we don't use that for that, and we'll learn how to do those. All right. Some elements exhibit a regular pattern of ionic charge when they form ions. This, you don't have to memorize this, but it will help you in the long run. If you were to memorize these, that would save you some time. Now, it's super not like required because they'll be given to you, but if you already know them in advance, it's just a little bit easier to do. But these for sure have these memorized. Okay, polyatomic ions. These are tricky. The ions that we have discussed so far are called monatomic ions. So like when we had chlorine lose 1, it came a -1. It's monatomic because it's one element. It's an ion because it has a charge. Polyatomic ions are electrically charged molecules, and that's a group of atoms bonded together. Oxyanions are polyatomic ions that contain 1 or more oxygen atoms. So we will deal a lot with polyatomic ions and oxy. So a polyatomic ion would be something like cyanide, and that would be the Cn -1. So it's a polyatomic ion because these two things are stuck together, but their overall charge is -1. So poly, more than one, ion, negative charge, polyatomic ion. An oxyanion would be like SO4 -2. That's supposed to be a capital O. This is sulfur bonded to 4 oxygens, and together they need 2 more electrons, so they become a -2. All right, let's see what's on the next slide. Okay, perfect. So here's a list of common ones. I've given you that list on Canvas to memorize, but here are some common ones. So ammonium, it's really the only one that's a polyatomic ion that has a positive charge. There is hydronium, but we don't really deal with hydronium as a polyatomic ion. So it is positive, but we don't usually call it a polyatomic ion. And we'll learn about hydronium when we talk about acids and bases. Okay, then we have the rest of these that are negative. So any of these with multiple, well, oxygens, doesn't have to be multiple. These are oxy anions. So there's oxygen, and they're an anion because they're a negatively charged ion. Okay, when metals bond with these anions, we have to make sure we know their charges and the charges of the metal. For example, if I have magnesium bonded to perchlorate, that is ClO4, I need to know the charge of magnesium is a positive 2. That's because it's in family 2. I need to know the charge of perchlorate because it's a -1. And then I have to make sure these two things add to 0. To make that happen, I have to have 2 of these -1s. So to do that, I would change the formula to MgClO4 and put a 2 right here. Because 2 -1s make a overall -2 charge. And then the +2 charge from the metal, that equals 0. Ionic compounds always have a neutral charge. And we can use that to figure out their formulas. Okay, let's try one of your own. So let's have sodium, Na, and let's pretend that it's bonding with SO4. Well, you pause it and try and find the numbers that go here and here. All right. Hopefully you were able to do that. So I would predict the charge of sodium to be a +1 because it's in family 1. Then SO4 I could find right here, and eventually you'll just find it in your memory, is a -2. So to make this equal 0, just like last time, I need 2 of my +1s. So I would put a 2 subscript with the Na, and I don't need any number with my SO4. Okay, we will do this over and over in the next couple days. But there's just a little introduction. All right, naming oxy anions. Wow, this is tricky, and I don't want to do it while I'm not looking at your faces. So I promise I will come back to how we name oxy anions. The good news is you're going to memorize them, and you'll be fine. But I'll teach you that face to face. All right. Types of chemical bonds. When electrons are transferred, ions form and ionic bonds result. Ionic bonds are electrostatic forces of attraction. So it's kind of tricky, but Na plus and Cl minus, they hang out together only because this plus and minus. It's not because they share an electron. They are just electrostatically stuck to each other like two magnets. All right. When electrons are shared, we call it a covalent bond. Compounds are classified as ionic or molecular or covalent on the basis of the bonds present in them. So let's talk about when you share an electron. So if I have hydrogen and I have oxygen, they are both wanting electrons. There's no metal here to lose and a non-metal to take. So what happens is O has 6 valence electrons, H has 1. So it donates, well, it doesn't donate, it shares with hydrogen or oxygen here, and then it shares with oxygen here. And now oxygen has the electrons it wants, hydrogen has the electrons it wants, and they benefit by sharing. So we would say that water is a covalent substance because the bond of the atoms are covalent. They're sharing. Now we have entire chapters about covalent and ionic bonding. So just the basics here. When ions are formed, ionic bonds are created. And they stick together because of electrostatic forces. A covalent bond is when the electrons share together. Okay, we'll just go 2 more slides. Ionic compounds, the metals are losers. Always remember metals are losers and they form cations. Nonmetals gain and they form anions. When a metal and nonmetal react, a transfer of electrons usually takes place. All right, metals and nonmetals generally form ionic compounds. A compound that contains ions and is held together by ionic bonds is called an ionic compound. This is just a lot of repetition. It's just a summary of basically everything we've said. There's a couple examples. Properties of ionic compounds. They're typically solids with high melting points, like table salt. They don't conduct, and when they are molten or placed into solution, they will conduct. Let me see how far. Oh man, this is going a lot farther than I thought. Ionic compounds are electrically neutral. That's what I was saying when the numbers up top had to equal 0. The formula of an ionic compound must have a ratio of ions such that the number of positive and negative charges are equal. These formulas are not molecular formulas, so they're slightly different. It doesn't, like when we write them out, we're not going to distinguish between one or the other, but they are slightly different. All right, so just an example, we did it before, but I have Al and I have O. Al is a positive 3 ion, oxygen is a -2 ion. So these have to equal 0. The way to do that is I need 2 3s and I need 3 2s. Then that equals 6 and -6. So what I would say is I need 2 of these and 3 of those. Now we can do the math, or we can think about a pretty cool thing that I call the drop and swap. Aluminum was a +3, oxygen was a -2. I can simply drop this number and swap its position. So I drop it and move it over. I take this number, I drop it and move it over, and that gives me my formula. And never take the plus or the minus in the bottom. And we'll talk about this a lot when I get back tomorrow. So many ionic compounds contain a polyatomic ion as the cation and anion are both. Treat them with as a discrete unit. So you can see what that means here. When we have a number with a polyatomic ion, it has to be put in parentheses and a 2 on the outside. So like if I had, what do I want here? So we'll just put aluminum and SO4. +3 -2. So we'll put 2 of these, and then we have to bracket and put 3 of those. And we'll go over this again a lot tomorrow. Okay, molecular compounds. There we go. We'll end with this one. They result when atoms share. They exist as discrete neutral molecules, usually formed by a combination of nonmetals. They often exist as gases and have low boiling points in liquids and low melting solids. So they're not something we study as much as ionic compounds in chemistry, but they'd be something like CO2, H2O, or your sugar, C6H12O6, things like that. They don't have a metal, so they end up having to share electrons instead of losing and gaining. Okay, I hope, make myself big again. I hope that was all right. It was probably super fast, but hopefully you're able to get through it. The rest of Chapter 2, we're going to talk about naming and formula writing. And hopefully by Friday you feel somewhat okay, and then Monday or Tuesday we should be rock solid. All right, have a good day, and I'll see you tomorrow.